So today I will give a talk about a problem that I've been working on for a few months, and I just wanted to share the process of solving the problem and the end result that I reached. I will outline first what the steps of this talk will be. So first I will tell you about the problem. That's some squeaky chalk. I will tell you about the edge cases of the problem to help understand what exactly is going on. I will tell you about the initial approach to solving it that you must do before any real work is done. Then there are two ways to solve the problem. There is the first approximate way that I found, where you can use a computer to actually solve it after you narrow down the cases enough. And then there is a more complete way of solving it, for which I'll give some mathematical intuition. Finally, I will show how the problem can be generalized and how the complete method may be useful for the general case. All right, so let's get started with the problem. Suppose you have 3 points. 1, 2, and 3. What we can do with these 3 points is we can try to connect them using some sort of network. Say, like that, like this, like this. Maybe there's a few extra lines in here that don't really help to connect the points, right? And there's a few things that we can say about this network. One thing that we can say about the network is how large it is, what I call the size of the network. And this is basically a measurement of how many lines did we use for the network, right? If you added the total length of everything we drew, even these extra bits, then how much did we use? So it's the total length. If we think of this network as maybe a network of roads between 3 towns, then that's how much concrete was used for the roads. Another thing we can talk about is something I call the delay of the network. And if, again, with the analogy of the 3 towns, the delay of the network is how long it takes you to drive between the 3 towns. So in this case, it would just be this length right here. And then you go back from this town up through here, and then back down to here. So it's the length of the shortest cycle between the 3 points. Shortest cycle. And what we can ask is, how do we make a good network? Where a good network is one that is both small in size and has a short delay, right? And the two of these quantities, though both of them somewhat measure the length of things in a network, they are sort of opposites. A network that is as small as possible will go out of its way to make itself shorter, right? It may not take the same shortcuts that the shortest cycle would take. And we can explore this by talking about the edge cases in the problem. If we only think about the size and if we only think about the delay, what happens? You can take a moment for yourself to think about what the solutions to each of these on their own would be. Let me check that the recording is working well. Great. All right. So what we can do is we can make a plot. On this axis, we will have the size of the network, and on this axis, we will have the delay of the network. And what we imagine is there's a network that's pretty good in delay, low delay, but not that great in size. And there's also some network that is great in size, but not very good in delay. And we can think of what each of these networks will be. So the easier one is the one with the smallest possible delay, right? So we have our 3 points, 1, 2, 3, and we want to draw the network that has the smallest possible cycle between the 3. And the solution is just to draw straight lines between the 3 points. The straight line is the shortest path, and we have the shortest path 3 times. That will give us the shortest delay. Hopefully that makes sense. Now, for the shortest size, however, or the smallest size, it's a bit more complicated. What the answer turns out to be is a network where there are 3 lines that meet at a single central point. And I haven't drawn it too well, but what's supposed to happen is that these lines at 120-degree angles to each other. And this minimizes the total length. And we can see what I was talking about earlier with the idea of the 2 of them being opposites. When we minimize the delay, the network tries to make the paths as straight as possible. But as a result, the total amount of road, the total amount of network, the size becomes larger. But if we try to minimize the size, the network goes out of its way, removes these shortcuts, but by the end is quite a bit shorter, quite a bit smaller. And the question that we're asking with the problem is, what's going on in between here? Because there should be a bunch of great networks that balance the 2 somewhat well, where both the size and the delay are small. Maybe not as small as at the edges, on the extremes, but still minimizing both. What happens then? So, before we answer that question, it's important to investigate what is going on with the smallest size network first. Why are there 120-degree angles? What's going on? So, let's look at it a bit further. So, let's draw a bigger triangle so that it may be easier to see what is going on. And we have a single point, and I won't draw the lines in for now. So, what we can think about here is if we label the points, say we have A, B, C, and this point is like O, then what we're trying to do is we're trying to minimize the sum of those 3 distances. So we have AO, we have BO, and we have CO, right? And as you might know, when you're trying to minimize something, it's often useful to take the derivative of it, because when the derivative is equal to 0, that's how you know when you're at an extrema. But what are the derivatives of these quantities? Well, they're absolute values, kind of in 2-dimensional space, but let's ignore the 2-dimensional space for now. If we draw a plot, and we think of this as sort of like a potential, then the distance from a point will be the absolute value. And say like we have point A here, and point O is some distance away, right? What's going to happen is, when we take the derivative is going to be pointing somehow like this, right? I guess it's not really the derivative, it's force is equal to minus the gradient of the potential. In this case, since the slope is positive, the minus makes it point to the left. And that makes sense. We're trying to minimize the distance. So in the case where A is here and O is here, it's almost like A pulls the point O towards itself, right? And we can think of this as a little force, A pulling on O. Similarly, because all the distances are being treated equally, B is pulling on O. Oh, not there. B is pulling on O, and C is pulling on O. So this potential produces a force, say A hat plus B hat plus C hat. And we want this force equal to 0, because that's when the potential will be minimized. When the forces are equal to 0, we know we can't decrease it any further. If it could decrease, then the forces would just pull it to the smaller direction. Now, we have these three forces. All of them are equal since the slopes are the same in every direction. The distances are all being treated equally. And as a result, when we have three equal forces, how do we balance them? Well, there's only one way to do that. You have 120-degree angles between them. And when you do that, the forces balance each other out. And let's draw it a bit bigger to make it more clear how that happens. So we have these three forces. We have our 120-degree angles, so like 60-degree angles here. And what we see is vertically, these two forces balance each other out. It's symmetric. And horizontally, we can do some trigonometry to see what's going on. So in order to find this component of the force, we're going to take the cosine of 60 degrees. We have two forces pointing this way, to the left, minus because it's pointing to the left, plus 1, and cosine of 60 degrees is 1/2. And this is indeed equal to 0, because the 2 and the 1/2 cancel, minus 1 plus 1 equals 0. And we see how the forces balance out in the horizontal direction as well. So that's why there are 120-degree angles in the minimum size configuration. One peculiarity is that there is a small case where the angles aren't 120 degrees. Say we have C and B somewhat like this, and A is over here. There isn't actually a spot for the angles to be 120 degrees, because anywhere in here, this angle will be too large. And anywhere in here, all the forces will be pointing in the same way. And what turns out to happen is that instead of a point somewhere inside the triangle, the point coincides with A. And the network will look like this. And we wonder how we can explain this. Well, there's sort of a problem with our idea of taking the derivative of the potential, because absolute values don't really work when you take the derivative at 0, because there's a sort of discontinuity there. But since I'm a physicist, we can sort of approximate it and think of the inside, very close to 0 of the absolute value, as being somewhat curved like that. And what we see is, the closer you get to a point, especially if you're directly on top of it, the forces get a bit weaker. And as a result, if the point coincides, then what we can have is we can have two of the strong forces from before pointing towards C and B, but we have a weaker force binding it to A, kind of holding it there. And as a result, the forces are still balanced and the potential is still minimized. This idea of forces and potentials and the force becoming weaker when the points coincide will be very important later. I've kind of sketched it out here, and hopefully it makes enough sense conceptually, because going through all the mathematical rigor of it really takes too long. let's see, what's next in my notes? All right, yes, we talked about that. We talked about the edge cases. We talked about the weaker binding force. So now we move on to the initial structure. All right, there we are. So for the more complete problem, we don't have the easiness of the idealized size or only delay options. We need to think of a general network that can minimize both well. Let's start with just a single point A. Well, I guess we can draw in B and C as well. So that's B, that's C, and here we have A. What can we say about the network? Well, from point A, there's going to be some sort of line that goes out until it reaches some point, and then the path will split. So first of all, we're minimizing the lengths within the network, the delay and the size. There's no reason for the lines to not be straight. If we make the lines straight, then the paths will be shorter, and we'll be decreasing both the size and the delay. There is no trade-off there, so we might as well do it. Similarly, these should be straight. Now, the next thing we can say is, where do these two paths lead? Well, the answer is pretty simple. There's only 2 points left for the paths to go to. One of the paths must go to B, and one of the paths must go to C. If one of the paths didn't lead anywhere, then there would be no reason to have it. We could just erase it and have the same network, but with better properties. So one of the paths leads to B, and one of the paths leads to C. Similarly, we can apply the same reasoning to B and to C. Starting from B, we reach some point, one of the paths will lead to A, one of the paths will lead to C. And from C, we go out, we reach some point, one of the paths will lead to B, and one of the paths will lead to A. And now, the rest is simple. These paths must connect, and the way they connect is with straight lines. So if we erase these arrows and connect the paths, we have a straight line there, almost. We have a straight line here, and we have a straight line here. And there is what our network will look like. And we haven't really said anything about where these points might be. These points can move around, and that is what changes the size and the delay of the network. In fact, we can see how the edge cases fit into this model. So, if we plot the size and delay again, we have this point, these two edge cases, some points in between. So, we have our smallest size network, which was from something like this. What's happening here is those 3 inner points that form a smaller triangle on the inside, they're all in a single spot. If we plot the minimum delay, then what's going on here is those 3 inner points for the inner triangle actually moved out and coincide with the outer vertices. And what's going on in between that we expect is what we expect to have is, I'm so good with words, something like this, where these inner points form some sort of triangle. And as we move along this line from minimum size all the way to minimum delay, we expect this triangle to grow and grow, right? As this triangle grows, we're adding a bit more line to the picture, increasing the size, but the paths become more straight. There's more of a shortcut to take, and as a result, the delay decreases. And we can see this more clearly if we label the distances a bit. If we label these three as the outer distance, outer, and we label these three as the inner distance, then what's going on is the outer distance is decreasing. It goes from being complete lines to no outer distance at all, and the inner distance is increasing. We're going from no inner triangle to everything being an inner triangle. And if we write formulas for the delay and the size, what we see is that the size is the sum of the outer plus the inner distances, and the delay is actually 2 times the outer distances plus the inner distance. Because these outer segments, when you do a cycle, are passed twice. Once when going out of the point, and once when coming back in. And this difference between the two formulas is what gives us this dichotomy. We can decrease the outer distance and affect the delay much more than the size. But decreasing the outer distance comes at the cost of increasing the inner one. Hopefully that makes sense. And we can see this qualitative picture of trade-off between outer and inner distances, between the size and the delay of the images or the networks, and how the inner triangle grows as we move along this line. However, this qualitative picture isn't enough for us to actually know how that triangle grows. Where does it move? Where do these 3 points end up? And that's where we get to my approximate solution. When we have a problem like this, where we know that there's 3 points somewhere, what we can try to do is have a computer place those points for us. And once it's tried enough things, maybe it'll find the best option. However, there's a bit of a problem. Let me check my notes to make sure I know what I'm saying. Right, approximate solution. And we have a bit of a problem. With our triangle and our 3 points, what we have is 6 degrees of freedom. Each of these points can move left and right, up and down. And that's a bit too much. Because say we only tested like 10 possible x positions and 10 possible y positions for each of these points. Because there's 6 degrees of freedom, that's already a million combinations. And though a computer is pretty fast, this is too slow for a computer to handle. So we can try to think of an approximate solution where we help the computer by reducing the number of degrees of freedom a bit. One step that we can take is we can rephrase these degrees of freedom. Instead of going left and right, up and down, a more useful way to think about it for the lengths is for these 3 points, are they moving towards or away from their nearest vertex? And what does the angle look like for each of them? So we have these sort of circles that these 3 points are on. And we're changing the size of the circle, and we're changing where the point is on the circle. So this is still 6 degrees of freedom, but there's something interesting going on. We have radii, and we have angles, 3 of each. When we set the radii to some value, then the outer length, O, is completely fixed. It's locked. No matter how we change the angles, the outer length won't change. But the inner length will be affected depending by how we turn these points. If we turn the points, for example, to something like this, then the network will obviously be a lot less efficient, right? And what you find out if you spend a bit of time working through this more mathematically, more formally, is that once you choose the 3 radii, the 3 angles set themselves. There's only one way to set the angles once you choose the radii. And as a result, this is actually only 3 degrees of freedom. The radii are a bit hard to work with the way you calculate the angles is very contrived. So one way to go around this is to rephrase the picture once more. Instead of thinking about left or right, up and down, or radii which fix the angles, you can think of a single central point, and you can think of the triangle and how large it is around that central point. And this will still be 3 degrees of freedom. And this central point can move left and right, up and down, and the triangle can get bigger and smaller. And with these 3 variables, the position of the central point and the triangle around it, which is pretty easy to calculate, this was enough for a computer to chug through the values and find the optimal path. Right. And this is pretty satisfying. We have this clean picture, a triangle expanding over time, reaching the outer points and eventually filling the entire thing. And we see the smooth transition from the smallest size to the smallest delay. But we don't know why it's working. Why do those configurations work? Why does this central point move like that? Why doesn't it move at the start and the central triangle just grows? The way we figure that out is with a more complete solution, without approximating it using a computer that does the brute force work for us. Right. So now for the more complete solution. And the way we reach a more complete solution is with the forces we were thinking about earlier. When we draw our picture once more with this plot, we can notice something interesting. If we're only minimizing the delay, what we're really doing is we're taking this line and we're going all the way down, as far down as we possibly can. If we do the size only, then we're going as far left as we possibly can. But what happens if we combine the two potentials? Well, what will end up happening when you try to minimize some combination of them is you'll minimize them along some angle. And what you will end up with is, if you go straight down, you will have some line and you'll find this point. If you go straight to the left, you'll find some line in this point. But when you go at angles, we'll be able to find other points along this line. And as we change A and B, we'll be able to find all of those points and all of the networks associated with them because we have these potentials that we can work with. To make the math a bit cleaner, let's, instead of using A and B, I will use 1 minus T S plus T d. So when t is equal to 0, we're only minimizing the size. And when t is equal to 1, we're only minimizing the delay. And when t is between 0 and 1, then we're minimizing some combination thereof, and we will find a point at some slope. Right, let's get to it. Let's try to minimize a combination of the two potentials using forces. I'll keep this around for now because it'll inform us what the forces will look like. So, let's draw our network once more. 3 points, and then inner points. Let's focus on this inner point. What are the forces acting on it that we need to balance? Well, there's a force pulling it towards here. How strong is that force? Well, we have the contribution from the size, let's say 1 minus t, and we have the contribution from delay. The thing is, this part of the path, when we're talking about delay, we pass over twice. Once when leaving for the cycle, and once when coming back in. As a result, the force from the delay will be 2t. When we think of the forces here, however, we still get 1 minus t from the size. But from the delay, each of these is traversed only once during the cycle. So we just add t. And now we can think of balancing these three forces. So let's redraw these forces to make it easier to see what's going on. So we have 1 minus t plus 2t. And then we have 1 minus t plus t, or just 1 in each of the other directions. We have 1 there, and we have 1 there. And we want these three forces to balance out. Well, first of all, as I've already drawn them, vertically, in order to balance out, these angles must be the same. Let's label them alpha. Horizontally, we can again do some trigonometry to figure it out. So, pointing to the left here, we have 1 minus t plus 2t. That's minus 1 plus t. Minus because it's pointing to the left. Pointing to the right, we have two forces, but we need to take the horizontal components. So we have 2 cosine alpha. And this is equal to 0. Now, what must alpha be? Well, we remember that there were actually 2 other points here. And they're in the exactly same situation. Everything here is symmetric. All of the forces are the same. And as a result, we find that alpha isn't just any value. These must all be 60-degree angles. So alpha is 30 degrees. So plugging in alpha is 30 degrees. We have root 3 over 2, canceling out the 2's. We end up with t is equal to root 3 minus 1. So it might not be obvious what exactly we just found here. What is this value of t? Well, these forces for this equilateral triangle we have found only balance when t, the slope between our two potentials, is root 3 minus 1. Which means that when, conversely, when t is equal to root 3 minus 1, we go from a single point at the center, suddenly, our single point at the center can expand into this equilateral triangle, and the forces still remain balanced. And that's what we actually see in our picture, in the computer, that the computer has found. At some point, with a sufficient slope, out of the central point, we have a triangle that expands. And now that we've seen this, we can qualitatively understand what's going on for the rest of the transformation. So, one last time, let's draw a plot. Size, delay. We start at minimum size with our network. Then, let me draw this a bit more convincingly. We should have a straight line like that, and then a curve like that. Once the slope reaches the critical value, √3 minus 1, instead of a single central point, we have an equilateral triangle. And this equilateral triangle can grow. The point at the center of it doesn't move, but the triangle still grows. And that's why we see this straight line part here. That's just the triangle growing, giving us a trade-off between the size and the delay. So let's mark a point somewhere around here, like 2. Eventually, the equilateral triangle grows too big. It reaches one of the points. Let's label that here, 3. So what happens at this point? Well, our perfect symmetry for these 3 points is now broken. We have reached this vertex, and what we may remember about forces, when the 2 vertices coincide, the force binding it becomes weaker. This force may be a bit weaker than these 2. And that's perfect for us, because that explains what happens next. This point stays there, but since the force is able to be weaker as the binding force, the other 2 take over. And now, what we see next is, oh, this chalk is really small by now. What we see next is, not that. We see an isosceles triangle. Now the symmetry is only between these 2 points. This one is not the same. And this isosceles triangle grows on its own. From an equilateral one, it grows outwards. Eventually, even this isosceles triangle grows large enough to reach another point. Like that. So this is somewhere around here. Finally, this last point moves towards where it needs to end up. And we end up with our minimum delay network. So, that's the step-by-step process. I'll play the video one more time so you can see these 6 steps as they happen with the way the computer approximated it. Now that we see why it happens with the balance of the forces, starting out, the forces pulling it all towards the central point, the forces being equal at all 3 points forming an equilateral triangle, the equilateral triangle growing until it can't grow no more, an isosceles triangle with a symmetry on only 2 points, and then finally the last point moving outwards until we have the full triangle with the minimum delay. That's the solution to our problem. It's a bit convoluted, and here I only showed you a qualitative description again, without much of the math that goes into it, since calculating these forces, balancing them, finding exactly where the points are is quite tricky. But it's not impossible. And what we can do next is think about where we can take this further. So, generalizing. Here we solved the problem with 3 outer points, which made the symmetry of the whole situation really simple. But we can think about networks that have more points. Say, for instance, something with 4. A network with 4 points has its minimum size with something like this. Again, we have 120-degree angles around here. And what happens when we try to change this network to minimize the delay instead? Eventually, we'll have a network that looks something like this, where we have straight lines between all the points once more. However, because there's 4 points now, there's some weird diagonals going on. And we can apply this force-based approach once again. These inner 120-degree points turn into triangles. Let's erase that. But these triangles won't be equilateral because there's no longer as much symmetry in this situation. Through here, we have 3 paths because you have the one going here, the one going here, and the one going here. But through here, you have 2 paths. You have 4 paths. One from here to here, from here to here, here, and here. Notice that instead of working with a cycle as you go from 1, 2, 3, 4, back to 1 points, we're really thinking about the delay being the sum of the distances between the points. If you started somewhere random and had to go somewhere else, on average, how long would it take? But the essence of the problem is still the same. And because we have 4 here and 3 here, it's no longer symmetrical for how many paths are going where. And as a result, the triangles will be stretched. And there's a whole new layer of complexity with the problem with 4 points, or maybe more points. It doesn't even have to be 2-dimensional. Maybe this point is somewhere out here in 3 dimensions. It's really limitless, and it's still a problem that I'm thinking about. And I hope you've enjoyed hearing about how I solved it, starting from the simplest problem, figuring out the structure of the network, figuring out a way to approximate it using a computer, and finally going back to the forces and seeing what they give us. Thank you.